What I wanted to do with this video is give you a brief introduction to the superposition principle. When I was looking for videos online, there were several that would mention using the superposition principle, but they wouldn't explain what the principle says. So I'll explain it to you here with this video, and then I'll share a separate video that shows some examples of how it can be used. So how this superposition principle works is, suppose we have this differential equation ay double prime plus by prime plus cy equals f1, and we have a solution to that differential equation. And then suppose we have this other differential equation ay double prime plus by prime plus cy equals f2, and we know a solution to that one as well. Notice here the two differential equations are exactly the same except for what shows up on the right hand side of them. One of them has this function f1, the other one has this function f2. Everything else about the differential equations are the same. When we have these two differential equations and the two corresponding solutions, what the superposition principle tells me is that for any constants k1 and k2, the combination of our solutions, k1 times y1 plus k2 times y2, is going to be a solution to the differential equation ay double prime plus by prime plus cy equals the combination of our right hand sides, k1 times f1 plus k2 times f2. Alright, so notice here, again, this is the key piece to all of it. The right hand side of this equation down at the bottom is a linear combination of the right hand sides up above. Some constant multiple of f1 plus some constant multiple of f2. There are two main ways that we can use this principle. One is, suppose we have this differential equation down at the bottom that we're trying to solve, and it's kind of an ugly equation because that right hand side is a mess. There's a lot going on the right hand side of this equation. The nice thing that this principle allows us to do is it allows us to break this differential equation up into smaller chunks. So if I don't want to solve this uglier equation down at the bottom, let's simplify things. First, solve this simpler equation up at the top, where the right hand side just involves f1, and then solve this other equation where the right hand side only involves f2. If I can find solutions to those two equations, then I can really easily write down the solution to my ugly equation by doing the combination of my easier solutions. The other way that we'll use this principle is we can use this principle to help us write down the general solution to a non-homogeneous equation. The basic idea is to suppose one of these two functions, f1 or f2, is identically the zero function. And in that case, the solution to the non-homogeneous equation shown here can be written as a combination of its solution, its particular solution that we may find using undetermined coefficients, along with the solution to the homogeneous equation. That may sound a little bit confusing, and it'll be clearer when I show you an example in the next slide, but basically what it boils down to is if I'm solving a non-homogeneous linear equation, the general solution will be a combination of the homogeneous solution with some particular solution that we might find using undetermined coefficients or other methods that we might learn. Alright, so let's go to the next slide and give a clear explanation of what this is all about. Alright, so let's look in a little more detail at what I was talking about at the end of the previous page. Suppose we have these two differential equations, ay double prime plus by prime plus cy equals 0, and then this other differential equation, ay double prime plus by prime plus cy equals f of t. Notice the left-hand sides of both equations are exactly the same, only the right-hand sides are different. For the equation on the left, we know how to solve these. These are the types of equations you were solving on your previous test. You find the auxiliary equation, and according to the whatever the roots of the auxiliary equation are, that tells you what your homogeneous solution will look like. On the right hand side, we already know how to solve these as well. That's what we learned how to do in section 4.4. We can solve this assuming f of t, this function on the right hand side, is one of those special cases that we talked about. Then we can make an educated guess at what the particular solution would be, and then find the appropriate coefficients that make it work. Okay, so these two equations individually we know how to solve using previous methods. Now, what I was describing at the end of the previous slide is that if you look at this differential equation down here, ay double prime plus by prime plus cy equals 0 plus f of t, the right hand side is now a combination of the right hand sides from my other two equations. If the right hand side is a combination of the right hand sides from those two equations, then I can write down a solution to this thing. The solution to this is going to be a combination of the solutions to those other two equations. So it's just yh plus yp. Now, notice the right hand side here is really just another way of saying 0 plus f of t is just the same thing as f of t. And so really what we've written down here is a solution to this equation that we have on the right up here, because 0 plus f of t is the same thing as just f of t. So this solution, y sub h plus y sub p, is also a solution to the equation we have on the top right. One thing we need to understand though, and this is what you'll see in the examples in the next video, this y sub h will contain arbitrary constants. In fact, it'll contain two arbitrary constants. Because if you remember, when we solve our auxiliary equation, we have something like, for example, we might have yh equals c1 e to the r1t plus c2 e to the r2t if r1 and r2 were distinct roots to the auxiliary equation. If we had repeated roots, then we'd have e to the rt and then t e to the rt. If we had complex roots, then we would have sines and cosines involved. All of those cases that we learned about give us the solution to this homogeneous equation, and this solution to the homogeneous equation involves two arbitrary constants. So when I write this solution down at the bottom, yh plus yp, that yh will contain two arbitrary constants. This is important because this solution here, like we said a second ago, is a solution to this equation in the top right, and this solution has two arbitrary constants. We know that solutions to second order differential equations should have two arbitrary constants, and this solution we have written down at the bottom has two arbitrary constants in it. So it turns out the general solution to any non-homogeneous equation can be written in this form. Okay, so let me just summarize here. All of this is just to say that if I want the general solution, not just a particular solution, but the general solution to an equation of the form ay double prime plus by prime plus cy equals f of t, a general solution to this non-homogeneous equation is just a combination of the homogeneous solution and a particular solution. Y sub h plus y sub p, where again y sub h is what you get when you solve the homogeneous, the corresponding homogeneous equation. Y sub p is what you get using, say, the method of undetermined coefficients. Alright, so you'll want to watch the next video carefully and you'll see how these things show up. And I will mention, like I said on the module, and in the video you're about to watch next, instead of calling this homogeneous solution YH, they call it YC. So don't let that throw you off. One last thing I want to show you guys before you move on to the next video to see some examples worked out. I want to return to the other application to the superposition principle that I mentioned at the beginning. The idea is that suppose I want to find a particular solution to this differential equation down here, y double prime plus 3y prime plus 2y equals 20 e to the 3t minus 10 sine of t. This is one of those situations I was talking about earlier where the right hand side is kind of ugly, but we can take advantage of some equations that we've solved earlier. If you look back in your notes from our lesson on undetermined coefficients, we solved these two equations up here. Y double prime plus 3y prime plus 2y equals 10 e to the 3t, and then y double prime plus 3y prime plus 2y equals sine of t. If you look back in your notes, we found a particular solution to each of these. We found that the particular solution to the first one was 1/2 e to the 3t, and we found that the particular solution to the second one was 1/10 sine t minus 3/10 cosine t. Now the idea of the superposition principle, other than what we saw on the previous slide where it helps us write the general solution, the other application that I want you to see here is that I can take advantage of these equations that I've already solved to find a particular solution to this equation down here at the bottom. The reason I can do that is if you look at the two that we've already solved, the left-hand sides are exactly the same. Y double prime plus 3y prime plus 2y. The left-hand side of this other equation is y double prime plus 3y prime plus 2y. And the equation we're trying to solve or find a particular solution for right now also has the exact same left-hand side. So the left-hand sides of all of these are exactly the same. The right-hand sides are different. But the interesting thing here is that these pieces are just variations or multiples of the right-hand sides from the topic examples. For example, up here, 10 e to the 3t. If I multiply it by 2 times 10 e to the 3t, I get 20 e to the 3t. This other function, I have a minus 10 sine t. Up here I have sine t. If I take my original function on the right hand side and multiply it by a negative 10 times sine t, I get this piece here. So things are looking a little bit messy and I apologize for that, but the basic idea is that this right-hand side on the equation we're trying to solve is a combination of the right-hand sides from the easier equations that we've already solved in previous notes. This first one, we're doing 2 times the original right-hand side. The second one, we're doing negative 10 times the original right-hand side. So this particular solution will be 2 times that first particular solution. minus 10 times that second particular solution. This is what the superposition principle tells us. If I want to solve this ugly right-hand side, I can break it down into smaller chunks and solve those first, and then the solution to the uglier one will be a combination of those easier solutions that we found. So then what this will look like, it would be 2 times my first particular solution, 2 times a half e to the 3t is just e to the 3t, minus 10 times my second particular solution. 10 times 1/10 is just 1, so I have minus 1 sine t. And then 10 times 3/10 is 3, so I have minus times minus minus, this is plus 3 cosine t. So the combination of our particular solutions gives a particular solution to this uglier equation here. Notice what I've written down here is just a particular solution. It's not the general solution to this equation. To find the general solution to this equation, I would still need to go through that extra step of finding YH. The general solution will always look the same. It's going to be your homogeneous solution plus your particular solution. And all we have so far is our particular solution right here. Okay, so if we go through a little bit of extra work to find the homogeneous solution, then we can write down our final answer. For the sake of time, I'm going to go ahead and stop this video here, and I want you to go ahead and go on to the next video that I've posted in this module to see several specific examples worked out in much greater detail than I've gone into in this video. In this video, the main idea or the main goal was to just show you guys how the superposition principle works and how we can use it. Alright, so now you should go see the examples worked out in the next video, and then you'll be ready to do your homework.